Fourier transform. So Fourier transform is mainly used to convert the signal into the frequency domain. Okay. The main purpose of learning Fourier transform is used to convert the signal into frequency domain. So Fourier transform will convert the signal from spatial domain. So the signal from the spatial, that is real world domain, into frequency domain. Why we need Fourier transform? Why we need to convert the signal from spatial domain to the frequency domain means, so in frequency domain, the patterns, edges, and the textures will be easy to analyze. Textures of images will be easy to analyze. So we need to convert the signal from spatial domain to frequency domain. So Fourier transform is used to convert that. The next one is Fourier analysis. Before that, we need to understand one thing. So the low frequency, on converting the spatial to frequency domain, the frequencies may be of low range, high range, maybe of mid range. The low frequency represents smooth regions. High frequency represents edge, sharper and fine details. Mid represents moderate one or a normal one. Okay. So Fourier analysis used to examine the filter frequencies. We are going to apply a known frequency sinusoid. A known frequency sinusoid to identify the impact of high, medium, and low frequencies to it. So I am going to consider S of x equal to sine of 2 pi fx plus psi of I. Okay, which is not mentioned here. This is the known frequency sinusoid. I am going to substitute 2 pi f with this omega. It represents the frequency. Okay, so this represents angular frequency. The normal f represents a kind of general frequency. So omega is equal to 2 pi f. So this phase pi represents the phase of sinusoid, and x represents a spatial coordinate. X represents a spatial coordinate. Okay. Okay, so the result of applying this sinusoid would be, we can understand a frequency of a filter pass, whether it is high, medium, or low frequencies. So this diagram represents the input S of x. H of x is nothing but a filter, and this is nothing but the output. So the S of x is considered as e power jwx or omega x. On applying into the filter, we performing convolution operation. H of x is the filter, S of x convolution H of x providing the O of x. The resultant would be an addition of amplitude and phase. So on applying the filter to an input signal, we would be able to know the amplitude as well as the phase value. Okay, so the amplitude can be either high or low. High amplitude represents the less visibility in edges. Less visible edges are represented when the amplitude is high, and we'll get sharper and finer details when the amplitude is low. And pi represents a shift. A shift means we will be able to see the movement of edges or movement of features in an image on applying the filter. Okay, so the original image will have the edges in certain part. On applying the filter, the edges would be moved. That is represented by the shift. Okay, so the next one is sinusoid S of x. We know that the sinusoid S of x equal to sine of wx, which is nothing but the sum of multiple sinusoids of the same frequencies, is still a sinusoid at that frequency, but with different amplitude and phase. That's what we have seen in the last slide as a result. Now, on applying the filter, O of x equal to H of x into S of x, what we got, instead of s equal to e power j wx, on applying e power j wx to the filter, we got a into e power j wx plus phi. So now I'm going to change s of x equal to sine frequency into input. So on applying to the filter, what we got, a instead of e, the previous result was e power j wx plus psi, right? So instead of e j omega x, I have converted into sine omega x, and the same phase will be considered. So same, the a can be high or low. High represents low visibility edges, low represents low visibility edges, high represents sharper details, and this is nothing but input frequency, and this represents change in shift. If you want to make it very complex, we can go of e power jwx. Okay, s of x can be represented as e power j omega x, or s of x equal to sine of omega x. So sine of omega x is simpler. E of j omega s is more complex because it is combination of both cos as well as sine. Okay, e power j omega s is equal to cos omega x plus j omega x. So if I want to omit cos, means I can directly simply rewrite as sine of omega x. Okay, so on applying e power j omega x, I will get this result. On applying sine omega x, I will get this sine alone. So the next one is yeah, this h of x is known as a filter. We know that, right? So on applying the Fourier transform on the filter h of x, I'm going to apply the Fourier transform on the filter h of x. I'm getting the result in the frequency domain, which is nothing but, so the input is represented as frequency and x, right? So those term alone will be omitted. A into e power j, the frequency as well as the spatial coordinate x is removed, the phase is retained. Okay, and compared to the previous result, this w and x is representing the input. So on applying the Fourier transform for the filter, those input alone omitted, the remaining a e power j phi is retained. So this is nothing but the pair notation. The pair notation means h of x represents the filter in the spatial domain, and the capital H of W represents filter in, omega represents frequency, filter in frequency domain. Okay, so h of x filter in spatial domain, on applying Fourier transform, it is converted into filter in frequency domain. Now we are going to see the Fourier transform in continuous domain and in discrete domain. In case of continuous domain, we will take integration. In case of discrete domain, we will take summation. Okay, h of omega is equal to the applied Fourier transform result of a filter. Okay, integration of minus infinity to plus infinity h of x into e power minus j omega x into dx. We know on applying the result of the output would be h into s. H represents filter, s represents input. So previously we have done for the convolution operation. Output is nothing but input into input convolution filter, right? So here the same, filter is h of x and the input is s of x. S of x I can either take e power minus j omega x, or I can take sine of x. So e power minus j omega x, nothing but it represents both cos as well as sine. So I can use both as a input. So filter into input into d of x. I am going to take with only one variable. So that is d of x. E power minus j omega x represents s of x, and h of x represents the filter. On applying the same to the continuous domain, so the integration is changed with the summation x equal to 0 n minus 1 h of x. The formula is bit changed, e power minus j 2 pi kx divided by n. N represents the length of the signal, right? So n represents the length of the signal. So this formula would be used in 2D Fourier representation. Now we are seeing only 1D. We are focusing only on x. So the same formula will be converted into 2D, the continuous as well as discrete also. And the discrete Fourier transform. This representation of discrete domain. This is the discrete Fourier transform, and it takes big O of n square operations. So the same DFT results can be applied in a fast manner using fast Fourier transform on the result big O of n log n. So the next slide represents the Fourier transforms of the separable kernels, right? So the Fourier transforms of separable kernels. The some of the kernel names are mentioned here. Box 3, box 5, linear, binomial, Sobel, as well as the corner, and the kernels are represented as a one dimension. So these are some of the transformation functions for this particular kernel. So observe the plot here. So box filter means the value is it passes the low frequencies. It passes the low frequencies. In case of binomial, look at this. So it also it smooths the box filter. Okay, the box filter result is smoothened here. The box filter result is smoothened, and it is also low pass frequency. Look at this so well. It passes only the high frequencies. Okay, the low frequency is blocked. Okay, on there is a change here. Okay, there is a complete vice versa. Here the zero point 0 we are starting the curve. In case of 0 0 there is no values here. So it passes the low frequencies. So Sobel means it passes the high frequencies. Corner is also passing the high frequencies, and it is also blocks the low frequencies. The Sobel is useful in identifying the edges. It is useful for identifying the corners. There is a difference between edges and corners. So if we have a set of fruits as an image, so the image outline is thickened in case of edges. So the corner, whatever may be the image, only the corner of the image will be focused when you apply the corner filter. Okay, these are the different filters, and its transformation is represented here. So the next part is we are going to see some three different types of filters, and its different part of signal frequencies, what it can be done or not done. So first one is moving average filter. Moving average filter, it is a low pass filter. It is a low pass filter, and it results in smooth signal. We already know in the first introduction slide I have mentioned low pass means smooth signal, high means finer edges and sharper details, right? So on applying moving average, the result would be a low pass filter, the low frequency, and it results in smooth signal. It doesn't remove high frequencies. Okay, since it is low pass, it doesn't remove high frequencies. The limitation is nothing but the limitation or the effect, it would result in ringing effect. Ringing effect means the high frequencies will have some kind of ringing edges. Then the binomial filter is also a low pass filter. When compared to moving average filter, it will remove some high frequencies. So the effect is not ringing, better than ringing, but not good. It results in aliasing. Next one is Sobel edge detector. It is one type of filter. It is a band pass filter. It is band pass filter. We have seen, right? We have seen in the previous slide. It produces the mid-range frequencies. So it is band pass, and it enhances the mid-range frequencies, and the drawback effect would be a loss of finer details. It may detect the edges, but some fine details such as tiny edges may disappear. That's what mentioned in the previous slide. So these are all some of the properties of Fourier transform. The first point represents the properties of Fourier transform. So the next one represents the different types of kernels. The moving average filter can cause the ringing effect due to uneven damping of high frequencies. Then the binomial filter also leave the high frequency details leading to aliasing. Then the Sobel edge detector, so make it challenging to detect the fine edge details. Okay, it focus with the mid-range frequencies. That's what mentioned in the slides. So the next one we are going to see about 2D Fourier transform. So far we have seen one-dimensional Fourier transform. So first of all, let's see 2D sinusoids. So 1D signal we have already seen, right? So S of x equal to sine of Wx. In case of 2D image, S of x comma y equal to sine of Wx plus Wy, right? So this is the example of 2D sinusoid. So on continuous domain, we are going to focus. Previously, we have focused only on Wx frequency of x alone. Now we are going to focus frequency of x as well as the frequency of y. So double integration. When compared to the previous formula, previously we have written h of x e power minus j omega x and d of x alone. Now it is changed as h of x comma y omega x plus omega y dx and dy double integration minus infinity to plus infinity. As usual, discrete domain can be represented with two summations h of x comma y, and previously we have seen e power minus j 2 pi k x, right? So now it is by n, and now it is m and n. So both m and n represents the width of the image, kx and ky represents it is discrete frequencies. Okay, wx, sorry, omega x, omega y represents a continuous frequencies. In order to represent it as discrete, we are going to consider kx and ky. Next one is Wiener filter. Wiener filter, the main purpose is used to reduce the noise and improve the signal quality. The purpose of Wiener filter is used to reduce the noise and improve the signal quality. So consider the image as a random collection of pixels. So random collection of pixels is combined to form a image. So which means each pixel. So if it is a pure black and white, then the range would be equal, right? So on considering the random pixels, so some pixel may be 1, some pixel 200, some pixel 150, some pixel 70. So this would form a clumsy random pixel of images. So this is not a proper image. So each pixel will be in different frequency domain and can have different strengths. So those strengths can be determined using power spectrum. Okay, P of S represents the power spectrum of omega x and omega y. The resultant would be expected magnitude. The magnitude squared, the squared amplitude at the given frequencies. Okay, so the given frequency is squared. Is squared. So this angular bracket represents average over random noise. Okay, so mean it is nothing but the average over random noise. So the next one represents the curve of discrete cosine transform, which we'll see it in later. So this line represents the low frequency and representing this blue. So the remaining sine wave we know, right? This is the sine wave. So I'm not going to focus on this sine wave now. Focus this blue line as well as this brown line, and one is straight, one is somewhat blended, right? So the straight one represents low frequency, which is smooth region, and the one which is increasing in frequencies is represents the sharper edges. So the Wiener filter is mostly used to clean the images. Next, we are going to focus on discrete cosine transform. So the discrete cosine transform will focus only on cosine. In Fourier transform, we represent S of x as sinusoidal form, as well as we have represented as e power minus j, which is nothing but cos plus sine, right? So I'm going to focus only on cosine, that is known as discrete cosine transform. So the discrete cosine transform use only cos, no sine, and it is mostly suitable for image compression. It is well suited for compressing images. That is the main purpose. If you want to compress an image, you can apply discrete cosine transform. So now we are going to see one-dimensional discrete cosine transform. So previously we have seen Fourier transform in 1D as well as 2D, right? So similarly, we are going to see 1D cosine transform. So I'm going to consider the pixels from 0 to n minus 1. On applying the discrete cosine formula, I'll get f of k equal to so and so. This f of k represents how much of cosine of each frequency k exists in the block. It represents the frequency coefficient. Okay, low frequency discrete cosine transform represents captures slow changes. Okay, high frequency discrete cosine transform capture fast change, right? The next one, each discrete cosine transform corresponds to the basis function. So first I'm going to see 1D discrete cosine transform and one in 1D discrete cosine transform. We are going to see the first basis function. So first basis function would be k equal to 0, which is nothing but a flat line which was seen in previous, right? So which represents the average brightness. So if you increase to next second basis function, the k would be 1, which is slightly curvy. So the optimal basis can be determined using cardinal log decomposition, KL decomposition. So the next we are going to see is 2D discrete cosine transform. 2D discrete cosine transform, we are going to take the blocks of pixels instead of one. So and previously we have seen 1D, right? 1D discrete cosine transform, we have focused with one value. Now we are going to focus with two values, summation of I equal to 0 to n minus 1, j equal to 0 to n minus 1. The same formula is repeated for j also. I and j represents the pixel position in the block. K and L represents the frequency indices along the x and y. So this is 1D discrete cosine transform formula only with I and k. This is converted into 2D discrete cosine formula, converted it with ij in terms of k and l. As I said earlier, ij represents pixel position, kl represents the frequency indices. Now 2D discrete cosine transform can be identified in two steps. One is one-dimensional DCT computed along each row, and the second step is 1D DCT, one-dimensional discrete cosine transform applied along each column. That's what represented. First, computing the density of each line, that is row, and computing the density of each resulting column. So 2D density can be done in two ways. So the density concentrate on most energy in the low frequency coefficients, so it is suitable for image compression. But some of the limitation is blocking artifacts. The solution for the blocking artifacts is waveless transform that we'll see later. So I hope you are able to see the images. Okay, so this is the original image. And this is the compressed image. On compressing, you could see there is blocking artifacts. The blocked artifacts represented in yellow color. Okay, so when compared to this region is somewhat blurred. Okay, so that is known as a blocking artifacts. So this is one of the major limitation. So next we are going to see the applications such as sharpening, blur, and noise removal. The traditional approach is linear filtering. Traditionally, we use linear filtering, and the advantage of linear filtering is it is simple and fast. But at the same time, the limitation is it will blur the edges, which is drawback to process the images. Now, the modern approach uses non-linear filter instead of linear filters, so it is more suitable for edge preservation. Edge preservation and some other variational methods like optimization problem is also used nowadays. And the next one, after compressing, the DCT is mostly used to compress, right? So after compressing, we have to check the denoising effectiveness, the denoise quality, how much it is denoised, whether it really affects the original image or not, is determined by PSNR, peak signal to noise ratio, and the high PSNR indicates less error, low PSNR indicates high error. In order to compute the error, we need original image as well as the denoised images. On comparing both, the error will be calculated. So the less error means high PSNR. Some other metrics is also used nowadays, SSIM. And if we don't have any original or clear image available, but at the same time we need to identify the denoising quality means we can use this NRQIA, sorry, NRIQA metric can also be used. No preference image quality assessment can be identified, NRIQA. That's all about Fourier transform. Thank you.